Yeah, so hello, ladies and gentlemen. My name is Kamil. I'm a Scala and big data developer at IMS Health here in Warsaw. And today I'm going to talk to you about continuous application that are done with help of Spark 2.0 or 2.1 sometimes. And huge disclaimer in the beginning. Continuous applications are still in the latest release of Spark, they're still alpha. So I'm going to be talking a lot about things that like this feature is not quite supported yet or will come in the future. It's not to say that this is a bad framework. Actually, because of some other already supported features, it will probably be a very good framework when it's fully complete. So what you want to do is you probably want to keep tabs on continuous applications, and that's what I'm here for. So the agenda is like this. I'll talk a little bit about the continuous applications, what are there, why would you want to write them. Say a bit like 3 words about some Spark 2 stuff, if in case you don't know it. By the way, who's used Spark 2 here? Oh, actually quite a lot of people, but I will still say that. Then I'll present you how to do input-output operations. Some easy stream transformations, some more advanced stream transformations with aggregations, windowing and stuff. And at point 6, there will be more of a painful point where I will say about all this stuff that is not supported yet, so that we don't make mistakes when we play around with continuous applications. Then the summary, and Daniel will take over. In telling you that, I will show you some examples from a case study application that I wrote, and I will put it on my GitHub today, which was basically like a loan management application with small elements of machine learning. The idea is that we're a company that loans money to people or other companies, and we expect to get this money back with some additional percentage. But might so happen that some people will default on the loans, and we want to keep this number of defaulted loans small. So the application, what it does, it predicts the possibility that given loan will be defaulted on, given that the client is from some country and some economic sector. So for instance, if, I don't know, shipbuilding in Poland fails drastically, the application will detect it, give us high default probabilities for the loans, and we might, for instance, refuse the loans to Polish shipbuilding companies because it won't pay us back. And code samples will be from there. And the last thing the application will do is basically, let's say that we're under some kind of stress testing and external auditors want to check if we don't have too many toxic loans. So it will take this already predicted probabilities and classify the loans in terms of very dangerous, not so dangerous, pretty healthy, very healthy. Okay. So first question, why use Spark? I believe John answered that question yesterday when he said that Spark changed the world. But basically, you know, I guess that everyone is more or less familiar with Spark. It's a highly distributed, scalable big data engine. It's the big data engine basically right now. It has some really powerful low-level optimizations. It has Tungsten, has Creo, has Catalyst. And on the other end, on that, you have a very high-level libraries like SparkML for machine learning, like GraphX for big graph processing. So on one hand, you keep the low-level optimizations, and then you can implement very specific things in the high-level stuff. And that, I believe, is the huge power of Spark. And then when it comes to how Spark does streaming, because that will be extremely important with continuous applications, streaming is basically processing data as it comes in small chunks and sending this processed data to our clients so that they have a real-time view of this data, as opposed to, for instance, batch computations. So how Spark does it is actually, it's not reactive, but it's when the source kind of pushes data on you, but it's actually in micro batches. So it, on constant intervals and configurable ones too, it monitors the sources. And when it detects some data on the source, it packs it in a small, into a small chunk of data and runs a batch on it, saving it to our outputs. So it's very close to element per element streaming, but not entirely. And what you want to do when thinking about continuous applications, you have to envisage this data as a table. like a, say, Spark SQL table, when these small batches arrive, you actually take them and append them to the table as new records. Potentially, since this is a continuous process, potentially into infinity. So you would have a unbounded table, as they call it in Databricks. And then when you process the data from that table, what you do is essentially create views on that table over and over, which also can be unbounded until you want to write it to the output, where you have to curb the data. And we'll see more of that. And so continuous applications, what they are, they're basically fusion between Spark streaming, as it was in 1.x versions, and Spark SQL with its high-level data processing tools, plus some additional facilities that will help you really a lot in terms of, for instance, reliability that we'll see. And so both Spark SQL and streaming existed before Spark 2, right? But you couldn't use them together in an efficient way. Spark SQL was basically just for batch computations, and you had these streams for streaming, but in order to create a data frame from them and to run some Spark SQL, you had to already do a huge for each, and that was a real pain, at least from my point of view. So now you have them together, and you have streaming on which you can run SQL queries for high-level data processing. And also it supports a lot of structured and semi-structured input types like Avro, JSON, Parquet, and Kafka, which you mostly had to parse by hand in the past with streams, right? So now these are the 3 lines about Spark 2.0. So what we will see in code samples heavily is in Spark 2.0 you have a new entry point instead of all these Spark context, SQL context, streaming context, etc. You only have Spark session and it has it all. So you'll see a lot of that. And also the Spark SQL AP migrated kind of from DataFrames to Datasets. So now DataFrame is just a type alias for dataset of rows, and they can be freely converted between one and the other. I also see a lot of that. And fun fact, Spark 2 is up to 10 times faster than Spark 1.6 was. There's actually data from a sample deployment at Uber, but you can see a lot of that on the Databricks page if you type Spark 2. They have a comprehensive study of how the operations are timed in 1.6 and 2.0, and it's mostly a huge decrease in time. We know what continuous applications are. We know more or less the idea behind what we will use from Spark 2. So let's look at the inputs. Now, for supported input sources, you currently, as this is again alpha, you currently have files from all the types of file systems, from local to via HDFS to S3, and also different file types, JSON, CSV, Parquet. Different codecs are supported as well, the most popular ones. You have a Kafka input, which I guess is really good for streaming, because Kafka is frequently connected with streaming. And you have a socket source, which is mostly for integration testing. It's just a stream from a TCP socket. So you can integration test stuff. And what is important here is that in ideal case, what we want to have is a traceable input, like let's say Kafka. While you're reading it, you can commit offsets, so if your application crashes, you can check, aha, I finished reading the source here, and reread stuff or read the stuff that you missed. And this is obviously beneficial, but we'll see how it really comes into play in terms of delivery guarantees here in Spark 2. And while you're reading the inputs, they come to you as a data frame, because they wanted to have a one universal interface for all inputs. And of course, data frame is the most generic type of data set that you can have. So enough talking. This is how it actually looks. It's a sample data source for Kafka from the loan management program and prediction that I mentioned. So you can see here what I'm doing is I'm taking the session, calling a read stream method on it. Then I have to provide the format, which is essentially the type of data source that I'm using, in this case Kafka. Then with option, I have to provide the format-specific configuration, so topics, so the bootstrap servers, serializers, the serializers. And then when I call load, I get a fully configured data frame from it, which I can then convert to a data set. These are the two last lines. So this is how it's done, and this is a data frame that already has a stream behind it, the unbounded table data frame. And then the output shortly. Well, it's kind of similar. When you have a data set and you want to save it, you call write stream. You have three main types of things. Sadly, Kafka is not really supported, what I learned from preparing for this presentation. But you have files, and files are supported pretty well. So if you just want to do files to files, you could actually start experimenting with these streams right now. You have a memory, which is essentially in-memory Spark SQL table. And you have console just for printing stuff to the console if you want to check what was in that stream. And as we wanted to have a traceable input, what's important on the output is that the saving data is idempotent. Also for delivery guarantees, also in a moment. And to finish the output, we have to supply something which is called output mode. So there are 3 of them. Out of these 3, only 2 are really supported. The update will be supported in the future. And if you think about this unbounded table for a second, what you'll be doing in complete mode, you'll just save the whole table. Of course, if the table is really huge, you don't really want to do that. But you can think of, for instance, if you heavily aggregate the data, that might be what you want to do. Then you have the append mode, which only saves to the output the rows that were appended in the latest microbatch. And finally, the update will in the future only save the one that were updated. So for instance, newly appended rows will not be saved in update mode if you want to choose it. And the very crucial thing, and the first mistake that I made while learning structured streaming, is that you cannot save a streaming data set or data frame as non-streaming, and conversely, you cannot save non-streaming as streaming. It will basically throw an exception. So don't do that. And in case you aren't happy with the few outputs that are already supported, you can actually write your own output, just implementing for each writer. For each writer is like if you ever wrote a custom writer for these streams, you know that there were some best practices like watch out what is run on driver, what is run on worker. Here you don't have that problem because this is basically the interface of that encapsulates all these best practices. So I encourage you to check it. And this is the example output. This is just the memory one. I have a data set. I'm calling write stream on it. Format is the type of output that we want to have. So in this case, in memory Spark SQL tables. Query name is, in that case, a table name. I specify the output mode, which is append. And I call start on it, which basically gives me a streaming query. Streaming query is a kind of handle for your streaming process that you can, for instance, cancel the process from, or you can subscribe to process events, like you can monitor the progress of saving partitions. So you can make your streaming also interactive, for instance, in the UI or in the console. And now that we can get data into stream and get it out of the streams, what kind of transformations can we do in structured streaming? Well, basically, almost all of them. So you have all the transformations that you're used to in terms of the streams. You have map, flat map, filter, drop, take. These are all implemented. But you also have, as an addition, the SQL queries that you can do with select where. It can be raw SQL. It can be the org Apache Spark SQL functions package. So for instance, you don't have to do a reduce to calculate a mean because you already have a mean in the Spark SQL package, right? You can just call this function and you're done. And we'll see an example of that. Aggregate all types of aggregations. That's a topic on its own, so I'll talk about it later. And also you can manipulate partitions with repartition coalesce, as you did in all the other, for instance, data frames. And here you have 2 examples of like very simple stream transformations on streaming data. And you can see that it's pretty much like Spark SQL, and you can mix the SQL part when it's convenient with the dataset part. So for instance, I do a filter which is typed, but then I have to manipulate some data behind the scenes, so I'm doing the SQL queries on it. And here in the second example, I'm doing first the SQL thing, and then I'm actually putting it in a form of a typed dataset. So this is really elastic, and you have all the high-level tools you might need. And what it also gives us is the ability to integrate it with, for instance, machine learning pipelines from Spark ML. Now, I have to say a huge disclaimer, not all machine learning pipelines will work with streaming. So you have to heavily test before you actually want to write it in, I don't know, some kind of POC code, I guess, right now, because some of them will use operations that they were written for non-streaming. So some of them might use operations that are not supported. But for instance, in case of a random forest regressor here, it worked. Yeah, this is the example where I took a stream, I extracted training data from it, fitted it, and basically used it to predict these probabilities of a loan being defaulted on. And it worked. But there is one problem with it when you use streaming. Does anyone see it? Well, the problem is that if you take the stream and you take training data from it, as well as you take the data to transform, you only get stuff from one microbatch. So training data from one microbatch might not be enough, to say the least. You need way more data to train your algorithm than one microbatch is. For instance, when you do it with Kafka, it's going to be really small. So for that, we have to, we have to do aggregations. Most notably, you could do a window-based aggregation, which is the topic of the next section. I will show how to improve on that. But the killer feature, from my point of view, is basically the delivery guarantees. Because you don't really have strong delivery guarantees in big data frameworks, right, until now. Not to mention Spark didn't have them until now. But what they did here is you have checkpointing to measure where your process failed throughout, where did you end before the failure. But if you have a traceable source that I mentioned and the idempotent sink, plus checkpointing, you can actually have an end-to-end exactly once delivery semantics, which is something I really haven't heard about in big data frameworks before. So if you fail somewhere along the way, right, you can retrieve the place where you're in from checkpoint, you can restart process, you can reread the data because the source is traceable, and even if you end up saving something twice, the same rows twice to the output, what happens is if it's idempotent, it doesn't really matter, right? So this, I guess, it's a huge feature. And since reactive streams are so hot right now, as it was said yesterday, I have to say that Spark streams don't have back pressure at this point. But this is actually looking through the Jira, that's probably going to come in next release with the whole reactive streams interface implementation. So it's probably also going to be a really nice feature. So aggregations, right? We know all the simple stream processing. Let's look at aggregations. So as I mentioned, you can do all the kinds of SQL aggregations of stream as well. You can group these streams by, you can order by. All this is available to you. You can run the Spark SQL functions, and also in Spark 2 you have this package with a very long name, org Apache Spark SQL expression Scala lang type package, where you have all the type functions for kind of type-safe aggregations on datasets. But the aggregation that you're most likely to do in streaming is actually based on a time window. So Spark Continuous Applications promote the idea that most of the time you actually have time embedded in your data. Meaning that, for instance, if you read data from Kafka, there's always a timestamp, right? For some NoSQL databases, also timestamp appended, and if not, if you need to use as your time the time when it came into a Spark stream, then you can basically just put it in there very easily. And so if you have time as your data, as just a column in a data frame or dataset, you can actually aggregate on it the same way that you did on SQL, and there is a window function for that, which basically looks like that. Here you have a data which is being processed for this machine learning algorithm, and you can see on the right that the window function is used to create a window on a timestamp, right? And that's how I kind of get a larger set of data for my machine learning algorithm, not just one microbatch, but can span into many microbatches if you use that. And this is also done with the thing that is shown in the last line, which is called watermarking. And it works like this. Normally, all the data you have in a stream is from one microbatch, right? but sometimes data can arrive late. I mean, microbatch is measured in real time, while you perform aggregation on the event time, so the time embedded in the data. And so it might so happen that the data with a timestamp that should theoretically fit in your microbatch arrives in the next microbatch or the microbatch after. And what you want to do here is do watermarking, so essentially the last line in the slide that I've shown. And if you declare a watermark on your time column, what Spark will do is it will cache your aggregations for a given period of time that you supply to Spark. And if late data arrives, even though it's already third next microbatch, Spark will basically update your aggregation and save it to the output. So you will not lose that data until the period of watermarking expires, because it cannot go on forever, because you just stuff your memory with it until then. Then when it expires, it will drop the aggregations for that particular aggregation, and if some more late data arrives, it will just be dropped. So I think it's a really nice trade-off, and it kind of handles a lot of problems for us. So again, this is here in the last line, you can see the watermarking being declared on the window column. And also something that SQL frameworks cannot do without joins. So in the past, when you only had batch data frames, you could join them freely. Now you can also join freely, but not everything is supported. So if you join batch with batch, it's batch, right? If you join streaming data frame with streaming, it's also a stream. But if you join a batch into a stream, what do you get? If you join a batch with a stream? Actually, no, actually a stream. Because if you think about it, if a stream is a series of micro batches, right? It's as if you joined this batch to every micro batch in the stream. So it gives you a stream. And that's the feature that I use to actually classify my loans in terms of how risky it is in the 5 classes or 6 classes. I took a data frame which represents the different classes of loan risk, and I basically joined it with my the data that already had this probability of default calculated. So you can see it's theoretically a huge operation, but really 2 lines. But I have to say that not all types of joins are supported specifically. You cannot still join 2 datasets. You cannot do full outer joins with streaming datasets. And some left and right joins are also not implemented currently, but it will come, they will come in the future. And the other stuff that is missing, as again, this is still alpha, right? It's a prospective framework, but it doesn't have everything in there. You cannot call, limit, distinct, you cannot chain aggregations, and you don't have some output modes on streaming data sets, or some of them yet. Also, Spark 0.2 is not available on all the platforms, though from the start, from the well-known big data platforms, but actually you can install it as an update on Cloudera already. You can install it on Mesosphere. So it does have some support, but not all the platforms supply it from day one. And just to summarize, I wanted to say that why you should be interested in it, though it's still a alpha project, is because it gives you all the power of Spark and good streaming mechanisms, while also giving you very high-level tools of data processing. I mean, from my experience, if you have to do some very complicated aggregations, it's going to end up in Spark SQL, right? So you can do that now on stream instead of handcrafting everything. You also have this you can also have this very strong exactly once end-to-end delivery guarantees, which is something you don't have with most streamings. And of course, it will gradually improve in the future. So I think it is a framework that you should keep your eyes on, because it will be an extremely good framework in the future, in my opinion. Yeah, and that was it. Thank you very much for your patience.